Can you see my screen now? All right, well, let's get started in talking about carboxylic acids and their derivatives. Good. So let's start by way of an introduction in just talking about the functional group itself and where you might find it. It says here that carboxylic acids are abundant in nature and are found in a variety of synthetic compounds produced by the pharmaceutical industry. The first four compounds on here are just naturally occurring compounds, so acetic acid, butanoic acid, hexanoic acid, and lactic acid. And it tells you that acetic acid is part of the component of vinegar, and it's responsible for the pungent smell that burns your nose a little bit. Butanoic acid, this is the smell that rancid butter produces. And then lactic acid, you're probably familiar with lactic acid if you've studied biology at all and the Krebs cycle. Anyhow, it's responsible for the taste of sour milk. Below, you see some pharmaceuticals. So these are some synthetic compounds like aspirin, which is a carboxylic acid derivative, and these other two here, even a compound that's used in the treatment of acne, which has a carboxylic acid functionality in it there. As far as the production of acetic acid goes, in the US, we produce about 2.5 million tons of that simple carboxylic acid every year. It's primarily used to produce the compound known as vinyl acetate, which is an ester. And we're going to look at ester nomenclature in this chapter, and we'll talk about where that name comes from. But vinyl acetate is used in things like paints in the paint industry. And so carboxylic acid derivatives like vinyl acetate are very common and play a central role in organic chemistry. And that's why the title of this chapter isn't just carboxylic acids, but it's carboxylic acid derivatives as well. So we're going to be looking at more than just carboxylic acids. We'll also spend a lot of time talking about acid chlorides, anhydrides, esters, amides later on. As far as the nomenclature of carboxylic acids go, monocarboxylic acids are named with oic acid. Well, there's a little caveat to that statement. I would say that that is for IUPAC. That's the IUPAC rules. So let's say you had, if you had methane, right, which is a 1-carbon hydrocarbon, if you drop the E, you end up with methanoic acid, okay? Now, methanoic acid is also acetic acid, right? Because methane only has 1 carbon in it, CH4, and methanoic acid, is formic acid, and methanoic acid also has 1 carbon in it like this, but there's also a common name for that, okay? And the common name for that would be formic acid, and we're going to look at the common names in a second. So if you had a 4-carbon hydrocarbon, right, 1, 2, 3, 4, like this is butane, and so we drop the E and it becomes butanoic acid, right? So we have that butanoic acid. Now, if we look at the next compound, you can see that this is what we call a bifunctional compound, right? Bifunctional. And the reason it's called bifunctional is because it has 2 functional groups. It's got a hydroxyl in it, and it's got a carboxylic acid in it. And the question then becomes, well, what is this compound? Is it a carboxylic acid, or is it an alcohol? And I've mentioned this to you before a couple times in this class, that it's based off of what's called the order of precedence. And here's the order of precedence right here for some, not all, but most functional groups that we would be interested in organic chemistry. So let's say you had, a ketone and an amine in the same compound. How would you call the compound? Would you say it's a ketone, or would you say it's an amine? Since ketone is higher in terms of priority, you would call the compound a ketone. And so in this compound that we're looking at, 5-hydroxy-4,4-dimethyl pentanoic acid, it has both a carboxylic acid and an alcohol in it, but you can see that nothing beats the carboxylic acid. It's the king of the castle, so to speak. And so we number this compound, giving the carboxyl carbon the number 1. So we have 1, 2, 3, 4, 5 in our longest chain. When we have a hydroxyl as a substituent, we call that a hydroxy. So a hydroxy. So we have 5-hydroxy, and then 4,4-dimethyl pentanoic acid. Remember, the hydroxy is going to come before the dimethyl because we ignore all prefixes except iso, cyclo, and neo. And so we're alphabetizing H versus M, and M comes after H in the alphabet. So there you go. Again, as I just pointed out to you, the carbon of the carboxylic acid moiety is assigned the locant position 1. And again, we won't see any exceptions to that because the carboxyl group is the king of the castle, so to speak. It's the highest in terms of precedence with respect to functional groups in organic chemistry. When you have the carboxyl group or the carboxylic acid group attached to a ring, it's named as an alkane carboxylic acid. The longest continuous chain in this compound is the 6-membered ring, cyclohexane. So this becomes cyclohexane carboxylic acid. The same thing would apply, let's say if you had, I don't know, something like this. If you had this, this would be called cyclopropane carboxylic acid, so on and so forth. Now, the next thing is something that I feel like the book is a little bit slack on, is the naming of the common names and the IUPAC names of carboxylic acid. So I have them summarized in a table that I took off the internet on the next slide, and I'll show you that in a second. So you can see that if you have one carbon, right, simply just one carbon in a carboxylic acid, well, like I just told you, that would be methanoic acid, right? If you have a one carbon alkane, that's methane, so methanoic acid, but the common name is formic acid. If you have a 2-carbon carboxylic acid, you would think ethanoic acid, right? Ethane is a 2-carbon hydrocarbon alkane, and so ethane, ethanoic acid, but here we have acetic acid. Then when you have 3 carbons, right, if we have a 3-carbon alkane, it's propane, so you would think propanoic acid, which is correct, but the common name is propionic acid. And then if we have 1, 2, 3, 4 carbons, you think, okay, well, if I have butane as a 4-carbon alkane, then I take the E and I drop that and I put oic acid, that would be butanoic acid. But you can see the common name is butyric acid. And then, of course, we have benzoic acid, which you've looked at before. So if you were confused about what I just said, well, I have it summarized here for you in this table. And you have to have this table memorized because I find that in our textbook, he just assumes that you kind of know this, and I don't know how you would, since most of you have never studied organic chemistry before. And so you have to know the nomenclature of the first 5 common carboxylic acids. So if we have only one carbon, the common name is formic acid, systematic name is methanoic acid, and again, you can see that as we go from 2 to 3 to 4 to 5 carbons, the systematic, which is the same thing as saying the IUPAC name, isn't very difficult, right? We go methanoic, ethanoic, propanoic, butanoic, and pentanoic, because how did we do that? We dropped the E suffix and we replaced it with oic acid. Well, what you'll see with the common names is that we don't have oic acid, we simply have ic acid as their suffix, okay? And then we have formic acid, acetic acid, propionic, right? And this one kind of annoys students, right? Because here we have propanoic and here we have propionic. They're 2 different words. You have to know them. The next one is butanoic and butyric, which again is a little frustrating because they're very similar. And the last one is valeric acid. Now, the way that you can remember that a 5-carbon carboxylic acid is valeric acid is you have the letter V, right, which kind of looks numeral, well, it is the Roman numeral 5, and it's got 5 carbons in it. So again, it would be wise, and that's my politically correct way of saying, is that you need to memorize this table, okay? Because it's used so much, and it's not simply used or solely used in the nomenclature of carboxylic acids. You're going to see this come up in the nomenclature of esters, acid chlorides, anhydrides, and amides as well. So very, very important. You could put a big star by this, but by now I'm sure you've all polished your memorization skills enough that you could look at this in a few minutes and have it down pat. And of course, the more you practice nomenclature, the more natural these will come to you. Okay, let's move on from there and talk about how would you name a dicarboxylic acid. I'll be honest, we don't look at a ton of dicarboxylic acids in this class. But since many of you are, interested in biology, and I think there's even some biology majors in this class, you'd probably be interested in the nomenclature of some dicarboxylic acids that show up relatively often in biology. And so If we have two carbons in a dicarboxylic acid, we call that oxalic acid. Now the IUPAC name for that would be ethane dioic acid. You're like, you need to write that down, Mr. Deon. Sure, it would be ethane dioic acid. If we have a 3-carbon dicarboxylic acid, it would be propane dioic acid. If we have a 4-carbon, it would be butane dioic acid. Sorry if you can't read my writing. And then we have 1, 2, 3, 4, 5 here. So this would be pentane dioic acid. And if you do a quick Google search, you'll come up, trust me, you'll come up with all the common names of all the dicarboxylic acids. And of course they go beyond this. But you have to know the common names as well for these ones that are on this slide here. So we have oxalic, malonic, succinic, and glutaric. Okay, so we're going from 2 carbons to 3 carbons to 4 carbons to 5 carbons. After 5 carbons, if you have a 6-carbon dicarboxylic acid, it's called adipic acid. So adipic acid, I could even write that down for you. So if we have 1, 2, 3, 4, 5, 6 like this, this is adipic acid. And the mnemonic that my students came up with, which makes no sense to me, a number of years ago they came up with this, and you know, of course, they love to share these kinds of things with me. It's OMSGA, right? Oxalic, malonic, succinic, glutaric, adipic. And I said, what does that stand for, you guys? And they said, I'll write it down. It's just very silly, but they said it's oh my stars, I don't know, exclamation point, go away. Okay, maybe we'll put the exclamation point there. So, oh my stars, go away. Again, I didn't come up with that. My students did. And hey, you know what? It can't be that bad because I still remember it. And that was probably, 4 years ago or something that they shared that with me. So there are the common and IUPAC names for dicarboxylic acids. Remember that these ones here, the ones that I have highlighted in yellow, these are common. Okay, these are common down here, and these would be systematic, or as I like to refer to them, this would be IUPAC. Okay, there we go. Well, with that in mind, let's see if we can name some carboxylic acids, some dicarboxylic acids, and we have some monocarboxylic acids here. I'm going to help you out with this just in the interest of time. And let's take this condensed structure and let's draw the full structure of this carboxylic acid, which has a total of, right, we have 1 times 3, or 1 times 3, so that's 3 plus 1 plus 1. So that gives us a total of 5 carbons. So we have 1, 2, 3, 4, 5. Okay, so the IUPAC name for this, or the systematic name, IUPAC name, would be pentane dioic acid, like that. And then if we want to give it a common name, you remember it was, what was it? Oh my stars, go away. So that was 2, 3, 4, 5, 6. So this must be glutaric acid. So we'll put that there. Glutaric acid. Next we have a total of 1, 2, 3, 4 carbons. And let's write out the full structure of that carboxylic acid, which will look something like this. We have 1, 2, 3, 4. And the systematic or IUPAC name of this compound, we have if we had a 4-carbon hydrocarbon, right, it would be butane. So we drop that off, and this would be butanoic acid, like that. And the IUPAC name is butyric acid. And the last one, hey, this is an old chestnut that you already know. And of course, C6H5, that's the same thing as a phenyl. Okay, so this is this compound here. So we have our aromatic ring, and then we have our carboxyl group here. So of course, you know this compound as benzoic acid, and that's actually the common name. So benzoic acid, common names are common for a reason because they're still used widely. But remember, I told you that when you have a carboxyl group coming off of a ring, you simply name the ring, which would be benzene, and then we add carboxylic acid to it. So benzene carboxylic acid, like that. I can tell you right now that if somebody said to me in the lab, "Hey, where's the benzene carboxylic acid?" Boy, would set me back for probably, a good 3 or 4 seconds to be like, "What are you talking about?" Oh, right, yeah, benzoic acid, jeepers. Okay, anyhow, let's look at some more problems here. It says here to draw the structure of each of the following compounds. First, we have cyclobutane carboxylic acid. So what are we going to do first? We're going to draw a cyclobutane. That's the parent of the molecule, and then we'll put a carboxyl group on that. So we have cyclobutane carboxylic acid, like that. The next one is 3,3-dichlorobutyric acid. Remember, when we have butyric, that means we've got 4 carbons. So we'll start by drawing the parent, which is butyric acid. So we have 1, 2, 3, 4 carbons like that. And on carbon 3, we have 2 chlorines. So again, this is 1, 2, 3, like that. And so we'll put our 2 chlorines out here, like that. And the next one is 3,3-dimethyl glutaric acid. If we think about our "oh my stars go away," right, we have 2, 3, 4, 5, 6. So we have 5 carbons, and we'll start by drawing glutaric acid. There's 1, 2, 3, 4, 5, like that. And then if we count like this, 1, 2, 3, 4, 5. Okay. So then on carbons 3, on the 2 carbons with the locant 3, we put a methyl group on each one of those, like that. Oops, that's kind of an ugly bond, isn't it? There we go, fixed it up. So 3,3-dimethyl glutaric acid. Okay, give me a thumbs up if you think you could do that with a little bit of practice, which is totally normal. As I told you, there's a lot of nomenclature in this chapter. All right, great. I can't stress it enough. The easiest way to master all this is simply to practice over and over and over, and you'll get better and better at it, I promise. The next one says provide an IUPAC name for the following compounds. I'll walk you through these. The first thing we're going to do with A is that we're going to number the longest carbon chain, giving the carbonyl, or the carbon of the carboxyl, the lowest number. So we have number 1, 2, 3, 4, 5, and 6. So this would be, if we had a 6 carbon hydrocarbon, that would be hexane, and we're going to drop that and we're going to replace it with oic acid. So this must be some kind of hexanoic acid. And you can see that we have a total of 4 substituents. They're all identical. We got 2 methyl groups here and 2 methyl groups here. 2 of them are on carbon 3, 2 of them are on carbon 4, and so this molecule would be 3,3,4,4, 3,3,4,4 tetramethyl hexanoic acid. The next one, same thing. Again, we find the longest carbon chain, and let me do that for you. So we start here, 1, 2, 3, 4, 5. If we had gone in the other direction, 2, 3, 4, 5. Either way, we're going to end up with a 5 carbon carboxylic acid, which would be pentane or pentanoic acid. And either way, we're going to get the same compound, right? You can see that we have our group over here, and this is a propyl group. So we could put that in here. We have a 2 propyl, and this again has 5 carbons, so it's a pentanoic acid. And if we put all that together, we get 2 propyl pentanoic acid. That's the IUPAC name of this compound, right? And that's what the question is asking for anyway. But in terms of the common name goes, I just want to put this bug in your ear because I know that I always have some students that love to look everything up on the internet in multiple sources. And there's nothing wrong with that. Nothing wrong with that at all. Is that sometimes if you're perusing the internet, you might see a different way of naming common carboxylic acids, which is where they take the chain, the longest carbon chain, and 1, 2, 3, 4, 5. So they call this the alpha carbon, the beta carbon, the gamma carbon, and the delta carbon, like this. So instead of calling this, 1, 2, so instead of calling this 2-propyl valeric acid, they'll actually call it, so they call this the alpha, beta, gamma, and delta. So they'll call it alpha propyl valeric acid. So I just want to float that out there just in case, and I don't think our book ever uses that, but in case you're the kind of person who just can't help yourself. So alpha propyl valeric acid. And I know that most of you are probably thinking, oh, please, for the love of Pete, Mr. Deon, don't throw another thing on our plate. I'm not going to ask you about that alpha, beta, gamma, delta, but just in case, again, you're the kind of person who likes to look around, you might see that, and now you'll know where it comes from. The last one, does anybody recognize this last compound? You're at the police station, they pull a curtain back, and they're like, do you recognize this carboxylic acid? I have a whole bunch of them up here. Anyhow, could anybody tell me what the stereochemical configuration would be at the stereocenter of carbon-2? Would that be R or S? I'll give you a second to look at it. Maybe I should erase these. It probably won't help. Does anybody have an idea? Sean says it's an amino acid. Exactly. It is an amino acid. In fact, this amino acid has a common name, which you'll have to learn if you take biochemistry. So this is L-phenylalanine. Phenylalanine, like that. Okay, but the IUPAC name, we're going to have to assign the stereochemistry. So this is going to be number 1. We have a hydrogen in the back, which is going to be group number 4. Then we have our carboxyl, which is going to be 2. This is going to be 3, so it's going like this. So the stereochemistry is S. And then we have an amino group at carbon 2, and we have a phenyl at carbon 3. And when you put all that together, you're going to get S2 amino 3 phenyl propanoic acid. And again, as Sean said, this is a naturally occurring amino acid. And later on in this class, we're going to do a whole chapter where we talk about amino acids, peptides, and proteins. It's chapter 25. And for many of you who will take biochemistry, probably in the spring or maybe later on, one of the first things you'll have to do is memorize all of the 20 naturally occurring amino acids and some others as well. And so you'd have to memorize the name and the structure of this compound, as well as this 3-letter and 1-letter abbreviation. But there you go. There's some more nomenclature. Let's talk about the structure of a carboxylic acid. By now, you are all fully aware that this carbon of the carboxyl group is sp2 hybridized. It's trigonal planar in terms of its molecular geometry. What else? We know that carboxylic acid is capable of forming very strong hydrogen bonds, including hydrogen bonds between acid pairs. If you remember in Chemistry 3102, many of you took that class with me. We did a whole lab where we discussed TLCs and we discussed, the polarity of a carboxylic acid, and I went over how it forms this kind of almost sort of 8-membered ring kind of system. And I could talk more about that, but I'll just leave that there. But it says here that as a result, carboxylic acids have higher boiling points than the analogous alcohols. I'll give you an example. If you have ethanol, so ethanol has a boiling point of around 78. It's actually 78.4 degrees Celsius. If you take the analogous carboxylic acid, which is ethanoic acid or acetic acid, whatever you want to call it, it has a boiling point of 118 degrees Celsius. So again, stronger hydrogen bonds, right, between those delta minuses of the oxygen and the delta plus of the hydrogen create those really strong hydrogen bonds and result in higher boiling points for carboxylic acids than the analogous alcohol. In terms of the acidity of a carboxylic acid, remember that carboxylic acids are acids. They are proton donors. That is the Bronsted definition of an acid. However, they're weak acids. They're not strong acids like sulfuric acid or hydrochloric acid or nitric acid. So they exist as a carboxylate salt in the presence of a base. Right? Remember, sodium hydroxide is a very strong base. Okay, So sodium hydroxide, strong base. And the pKa of a carboxylic acid, pKa is around 5, and the pKa of water is around, 15.7. So if this is our acid, right, and this is our base, this is our conjugate acid, and this is our conjugate base, well, the equilibrium is always going to lie to the side of the weaker acid. And so the equilibrium is going to lie to the side. You're going to get total deprotonation of the carboxylic acid by that strong base. Now, you might be wondering, how would I name a carboxylate salt? And the answer is you replace the ic suffix with -ate. And that's, it says here carboxylate ions end in the suffix -ate. So we take the ic acid and we replace it with -ate. So we have sodium benzoate. And let me just write this in here, is that when you're doing this, the first step should be to name the cation first. Okay, we name the cation first. And since it's a sodium cation, right, we never change that. So it's just sodium benzoate. Let's talk more about the pKa and the relative acidity of carboxylic acids. In water, carboxylic acids only dissociate slightly. Say you have something like acetic acid, it only dissociates 5% in water to form the carboxylate, right? This again would be acetic. Oops, where's my pencil? Come on, there we go. Right, this is acetic acid, right? And then this is hydronium, like that. Hydronium is a much stronger acid than acetic acid, which has a pKa, let me write it up here, pKa is around 5, around 5, and the pKa of hydronium is around, negative 1.7 or negative 2. And so you can see that the equilibrium is going to lie mostly to the side of what? The weaker acid. Okay. Again, the pK of most carboxylic acids is around that 4 to 5 range, and you should have known that already because we spent so much time talking about this, in chapter 3, I believe it was, in Organic Chemistry 1 is our acids and bases chapter. Now, again, if we compare the acidity of a carboxylic acid to something like HCl or sulfuric acid, these are really strong acids. And so comparably speaking, they are weak acids, but everything is relative. If you compare the acidity of a carboxylic acid to an alcohol, wow, it's really acidic. If you compare acetic acid versus ethanol is what? Or acetic acid is around 10 to the power of 11 times more acidic than ethanol. So that's a big difference. Now, if you look at the conjugate bases of both of these, okay, so if we look at the conjugate base of acetic acid, it would be what's called the acetate ion, and that's what's shown below here on the slide. You're like, isn't that what I see right here? Yeah, you're right. Okay, so this is called an acetate. Okay, and that's the common name. The IUPAC name would be ethanoate. And then if we look at the conjugate base here, okay, we have that oxide, ethoxide. So we have ethoxide, like that. Okay, well, if we think about, we'll go way back to our areo, right? Areo. What differentiates, or how would we explain or rationalize the large difference in acidity between these two compounds? Is it based off of the atom? Well, absolutely not, because the negative charge on both of them is on an oxygen. Is it based on resonance? And the answer is yes, it is based on resonance, right? If you look at the carboxylate, the acetate in this case, it has this beautiful resonance structure where that negative charge is delocalized across those two oxygens. What does that do? It stabilizes the conjugate base relative to an ethoxide, which doesn't have any resonance contributors. And remember, the more stable the conjugate base, the more acidic your acid is. Let's look at some more examples of the acidity of carboxylic acids. Remember that electron withdrawing groups, right? If we go back to our areo, right? Electron withdrawing groups, let me use the yellow here, right? Those are going to have an inductive effect, right? Because they're going to pull negative density towards themselves, and they're going to help to stabilize the conjugate bases of any acid. So the stronger and or closer they are to an acidic proton, the stronger the acid. We go from this carboxylic here, acetic acid, then we go to alpha chloroacetic acid, to alpha dichloro, to alpha to trichloroacetic acid, so on and so forth. What's the effect as we go from 4.8 to 2.9 to 1.3 to 0.9? Is that we're adding more and more and more chlorines. Well, you know that chlorine is electron withdrawing, right? We've looked at that several times in this class. And so you go from having one dipole to having two to then having three. So it's an additive effect, that inductive effect. The more electron withdrawing groups you have, again, I'm repeating myself, but the more it stabilizes the conjugate base. Okay. Now, I'm going to draw a carboxylic acid here, and I'm going to draw what's called trifluoroacetic acid. So if I was to replace all three of those chlorines on the carboxylic acid that's above, so if I compare these two carboxylic acids, if I compare these two carboxylic acids, can anybody tell me which one would be stronger? Would it be the trichloro or the trifluoroacetic acid? Just what's your intuition on that, based on everything that you've ever learned in your life? Yeah, absolutely, absolutely. So all three of my students that responded to this, now 4 students, you're all correct. Okay, the answer is trifluoro. Why? Because fluorine is the most electronegative element there is. Okay, so in fact, the fluorine is more electronegative, so it's going to stabilize that carboxylate even more. And so the pKa of this compound is actually 0.23. Okay, so even lower than the pKa of trichloroacetic acid. And this is called trifluoroacetic acid. Okay, and we call it TFA. And you're actually going to see TFA come up later on in this class, not in this chapter, but later on it will come up in the chapter on amino acids, peptides, and proteins. In TFA, I've used TFA, Avogadro's number of times, and the effect that acetic acid and vinegar has on your nose. Well, if you ever get a whiff of TFA, take that and multiply it by 20 times. It's much, much worse. Okay, and that's because it's a stronger acid. The next two examples here, if you compare this compound, them boxing in green now with these two compounds, at least I'm trying to box them in here, as we go from 2.9 to 4.1 to 4.5, the whole point here is that as the electron withdrawing group gets further and further away, the effect on the acidity is less and less pronounced. Okay, and you can even see that the pK of this one here is very close to the pK of acetic acid. And so once you get out to about the gamma carbon, if you have an electron withdrawing a substituent, it almost has like very little effect, almost no effect at all. One more thing is about electron withdrawing groups on benzoic acid. If we have a strongly electron withdrawing group, like a nitro group, right, that's going to lower the pKa of benzoic acid. Benzoic acid has a pK of 4.5. And then, if you put different groups on there, you can just see that the more electron withdrawing group you have, or the more electron withdrawing a substituent is at the para position, for example, it's going to lower the pKa. Now, I could keep talking about that and talk about why it has to be in the para position, but you should probably be able to answer that on your own by now. And in the interest of time, we're just going to keep forging ahead here. And let's try another practice problem, which asks us to rank each set of compounds in order of increasing acidity. It's kind of hard to tell here, but there's actually 2 questions on this slide. The first question is this one here. So we're going to compare these 3 carboxylic acids, and then finally we're going to compare these 5 benzoic acid derivatives. The first thing we're going to do in the first question, I think, is draw all of the compounds. They're all derivatives of butyric acid. And so we could start by drawing butyric acid, 1, 2, 3, 4, like that. We could spruce that up a little bit, couldn't I? That's not very pretty. There we go. And we could just copy that. Copy that. Come on, paste. Paste. There we go. So, son of a gun. Now we've got all these butyric acid molecules. You've probably got them drawn faster than I do. Okay, so first we'll do 2,4-dichloro. So we'll put on some chlorines. So we have 2,4-dichloro. Then we have, what do we have? 2,3-dichloro. So it's 2,3-dichloro. And last we have 3,4-dimethyl. Yeah. 3,4-dimethyl. Oh, I thought it was 3,4-dichloro. Why don't I just do this? CH3. CH3. There we go. Okay. Now, in terms of, these three, I think that you probably all have a knee-jerk reaction as to which one of these is going to be the least acidic. Okay, who could tell me which one of these three will be the least acidic? Yeah, exactly. David just wrote methyl, and Sarah put last one. You're both correct, right? This one is going to be the least acidic because it doesn't have any electron withdrawing group. So least acidic, and we'll put here no EWG, no electron withdrawing group, right? How are these two different than the 3,4-dimethyl butyric acid? Is they both have chlorines. Chlorine is an electron withdrawing element, and if we think of areo, maybe I should just help you out here a little bit more. Maybe if we put this here, and then for these two compounds, we can use areo, right? And it's going to be based off of induction. Now, who could tell me, if I look at 2,4 versus 2,3, which one of these do you think is going to have a stronger inductive effect, rendering the acid more acidic? The first one or the second one? Exactly. It's the 2,3, 2,3-dichlorobutyric acid. So we'll put here most acidic. And this is based off of proximity of electron withdrawing groups. It's nothing more than this chlorine, right? You have a chlorine at carbon 2 in both of them, but this one's at carbon 3 and this one's at carbon 4. So this one is the winner. Winner, winner, chicken dinner, so to speak. Anyhow, give me a thumbs up if you just understand that. And I'm assuming at this point, most of you are probably going faster than me and just are kind of like, yeah, get on with the show, man. I know. I figured this out a long time ago. Didn't you teach me areo a long time ago? Well, it's always good to kind of review the content a little bit. The last one, I'll kind of help you out with this one. If we look at all of these different groups and their ability to withdraw electrons, the two, strongest electron withdrawing groups I see are a nitro and an acetyl group. And of course, a nitro is even more electron withdrawing. So this is going to be the most acidic. This will be the second. Remember that bromine is electron withdrawing based off of electronegativity, and it's electron donating based on resonance. But if you look at the last two, the methoxy and the methyl, right, those are both electron donating. Okay, so that's going to have the opposite effect. All right, and so who could tell me which one will be the weakest of all the acids? Would it be the one with the methoxy or the one with the methyl? Which would be the weakest, methoxy or methyl? And it's not a trick question. What do you think? Would it be the methoxy or the methyl? Which one has the ability to donate electron density more, a methoxy or a methyl? Yeah, the answer is the methoxy, right? This is going to be the weakest one because the methoxy has two lone pairs that it can donate the electron density to destabilize the carboxylate, whereas the methyl can only donate electron density via hyperconjugation. Okay, it doesn't have that resonance capability. So there we go. Okay, so we'll put here strongest electron withdrawing group, and then we'll put here strongest electron donating group, like that. Okay, and if you're wondering, how did you rank, how did you figure out the order of the strongest and the weakest, or whatever in this one? You might want to go back to the chapter on electrophilic aromatic substitution, which was chapter 18, and you could review that content if you need to. Okay, let's get into my favorite, material in the chapter, which is synthesis. And you can see that was quite a bit on what have we covered already, and it's almost 9 o'clock in the morning. We've covered some nomenclature, and we're still not done. We have a lot more nomenclature in this chapter, but we've covered some nomenclature, and we've covered some of the pKa, or the relative acidity of carboxylic acids, and we actually looked at it from a pretty qualitative, viewpoint, of course, quantitative to some degree. And anyhow, so let's get into section 20.4, which deals with the preparation of carboxylic acids. And the good news is we're going to start with some review. These are all reactions that you've learned already, and it says here in earlier chapters. The first one, which I think is probably the first time you learned how to make a carboxylic acid, was the oxidative cleavage, or the ozonolysis of an alkyne. If we take an alkyne and we treat it with ozone followed by water, we end up with a couple of carboxylic acids here. The next one is the oxidation of a primary alcohol. Now, they only show one way to do that, and that's to treat it with chromic acid, which is made by treating sodium dichromate with sulfuric acid and water, which actually creates chromic acid in situ. But it says here, a variety of strong oxidizing agents can be used to oxidize primary alcohols to carboxylic acid. There's one other one that we learned, and that was to use, I'll write here, or. It's a two-step process. You can use potassium permanganate, okay, KMnO4, and water, and heat that up. And then in the second step, you treat that with acid, because the first step produces the carboxylate. So that's another option. And then the next thing that we learned is a benzylic oxidation. It says oxidation of an alkyl benzene. An alkyl group on an aromatic ring will be completely oxidized to give benzoic acid. Why? Because it has a benzylic, this is cumene or isopropyl benzene, but it has that benzyl proton, which is necessary. It says here the benzylic position has at least one hydrogen atom. And so we can oxidize it using that chromic acid, which is produced by mixing sodium dichromate, sulfuric acid, and water. And you could also use this method. So we'll copy that in here. Yeah, that'll work as well. So we've got a couple options there. All right, so those are ways that we've learned to make a carboxylic acid. Let me show you a couple of neat ways to make a carboxylic acid. The first one we already looked at briefly in the last chapter, and I'm not going to, anyhow, is the hydrolysis of a nitrile. So if we take a nitrile, remember, if you take cyanide, you can react it in an SN2 reaction to produce a nitrile. And if we take a nitrile and we treat that with just acid and we heat that up, so aqueous acid, and we heat that up, we produce a carboxylic acid. Now, you might be wondering about the mechanism for that reaction. That's something that we'll look at later on in this class. But overall, if you know this reaction, you know that you could produce now a carboxylic acid via a two-step synthesis from an alkyl halide. So if we were to take benzyl bromide, which is the compound on the bottom left, and it says here cyanide, now that would of course have to be, you'd want to write sodium cyanide. And since this is an SN2 reaction, you could even choose a polar aprotic solvent like acetone or DMSO or something like that. I'll just write a solvent in there. Okay. And then you would take that nitrile and you would heat that up with acid and water. And now you've made a carboxylic acid. And you've also added one carbon to the overall molecule, right? You started out with a 7-carbon molecule, and now you have an 8-carbon molecule. Kind of a neat synthesis. The next one is one I've done many, many times in my life, is the carboxylation of a Grignard reagent with carbon dioxide. In fact, this is something that we do sometimes in the lab here with the students at UCCS. And what we do is we take a Grignard, and this is the Grignard reagent shown right here, and it's not exactly shown how you're used to it. But remember, if you have RMG, BR, remember I told you can think of that as being R minus and then MG, BR plus, like this. So here's your R minus, okay? And if you treat that with solid CO2, which is a fancy way of saying dry ice, I didn't mean to delete that. if you treat this with dry ice, okay, and that's what this is right here. This is nothing more than dry ice. Okay, so right here, dry ice. Well, dry ice is actually a very good electrophile. Okay, electrophile, and a Grignard, of course, is an excellent nucleophile, and so it's going to attack that to make a carboxylate. And so overall, this is a two-step process. First, you form the Grignard, you treat it with carbon dioxide, again, dry ice, and then you protonate that. And there you go, you have yourself a carboxylic acid. Now, the overall process looks something like this. Gives us a second method to convert an alkyl halide, or here we have an aryl halide. Maybe we should put that in here too then. Alkyl or aryl, okay, halide into a carboxylic acid. So we start with this compound, which is bromobenzene, and we magnesium and diethyl ether. Right, it's kind of a Halloween-y experiment here. Anyhow, and we make phenyl magnesium bromide. So this is phenyl magnesium bromide, like that. And then of course you can think of that as being like a phenyl anion. Okay, and then we have our MgBr like this. Okay, then what's it going to do? It's going to react with the carbon in carbon dioxide, and I'm leaving out my lone pairs here, so you have to bear with me. But then you make the carboxylate, okay? So that would give you the carboxylate, which looks like this, right? And then in the last step, you treat it with H3O plus and you protonate it, all right? Pretty cool. And this is a very common way of making carboxylic acids. Again, not just because I've done it many times in my life, but it's just still very widely used in organic chemistry. So nothing, you know, super new in terms of, you know, the scientific community, but something that's very, very effective and still used a lot to this day. Okay, well, with that in mind, all of that in mind, we're going to strap on our synthesis and our nomenclature hat at the same time, because in this question, it's asking us how to do these syntheses, but it doesn't provide any structures. It simply provides some names. And first, we're going to take, if we had some ethanol, and you can all draw the structure of ethanol, and we wanted to make acetic acid, which is the common name of a 2-carbon carboxylic acid, how would we do this? Well, this is simply the oxidation of a primary alcohol, right? We want to oxidize a primary alcohol to a carboxylic acid, and there's 2 ways that we can do this. We could either use sodium dichromate in sulfuric acid and water, or another option would be a 2-step process where we treat it with potassium permanganate and water, and we cook that up, and then in the second step we do a workup with aqueous acid. So that's the first one. The next one is we want to take toluene, and you should all be able to draw toluene, which is methylbenzene. Toluene is the common name. Okay, we want to take that and we want to convert that to benzoic acid. And since we have those 3 benzylic protons, we can oxidize that very easily. In fact, if I back up a few slides ago, that's, you know, what we're doing right here, okay? We have, except now we have 3 benzylic protons, and so we can use either of those sets of conditions that you see right here. And if you're wondering, you know, hey, aren't those the same conditions that we just looked at? The answer is yes. Okay, the answer is yes. So let's go back here, and we'll just copy these in here. So like that, copy and paste. Those are our 2 possibilities. Maybe I'll move them up here a little bit. Okay, the next one is we want to take benzene and convert it to benzoic acid. Here it gets a little bit more interesting because we're actually going to change the carbon skeleton, right? If we start with benzene, which only has 6 carbons, and we want to make benzoic acid, well, benzoic acid has a total of 7 carbons. So I'm going to need to have some more space here. Let's delete all this. Does anybody have an idea of how we might do this? Well, I'm writing it down. How might you do this? Does anybody have just any kind of idea how we might do this. Somebody says with cyanide, the problem with cyanide is that there's no way to go from, benzene to well, this would be called benzonitrile. There's no good way to go from benzene to benzonitrile using cyanide because you can't do an SN2 reaction on an sp2 hybridized carbon. Okay, so Andrew is saying, maybe do a Grignard, right? Maybe do some Grignard chemistry. Could we make, so what he's saying is if you could make this compound, jeepers, let me try and move this slide up. Yeah, I know it's not pretty, but just so I can have more room here. What Andrew is saying is, he's saying if you could make this compound, bromobenzene, then you could treat that with magnesium in diethyl ether, and then you could treat it with carbon dioxide, right? Then you'd end up with the carboxylate. Okay, you'd end up with this carboxylate, and then finally you could treat it with H3O plus to give you benzoic acid. So then the question becomes, how do you do the bromination? This is something that we looked at, but it was a few chapters ago. Could anybody tell me, what kind of strategy you might use for aromatic bromination on benzene, which is not activated whatsoever? We're going to need bromine, but we're going to need something else. Maybe a catalyst? Yeah, exactly. So Sarah and Andrew are saying aluminum tribromide. Sure, that works. Sean is saying iron 3 bromide. That works as well. Yeah, absolutely. So why don't we put that in here? We'll say methyl bromide and the Lewis acid catalyst. We'll put AlBr3 here. And there we go. We're going to do an aromatic bromination. Then we do our Grignard reaction. We treat it with carbon dioxide as our electrophile. Then we treat it with an acid, and there you go. That's it. The next one, I don't even have enough room to solve the next one, do I? Anyhow, so we have 1 bromobutane. Let's draw that at 1, 2, 3, 4. 1 bromobutane, and I want to form pentanoic acid. 1, 2, 3, 4, 5. Oops, I'm really running out of space here. Let me clean that up. Let me draw it this way so I won't run out of space. 1, 2, 3, 4, 5. Well, I'll go over this one with you kind of quickly. You can see that you're adding a carbon. Right here we have 4 carbons. In here we have 5 carbons. So this is, since this is a primary, right, this is a primary alkyl halide, this would be a really good candidate for what David was suggesting earlier on. And what he was saying is in the first step, why don't you treat it with sodium cyanide, right? So if you treated it with sodium cyanide in a polar aprotic solvent, that would give you the nitrile, and then you could simply treat that with acid and heat that up, and that carboxylic acid. That's one way of doing it, okay? And there's nothing wrong with that at all. In fact, I'd give that 100%. I'd try it myself. But another way you could do that is just to take that primary alkyl halide in the first step, treat it with magnesium and diethyl ether, right? Second step would be to treat it with carbon dioxide, do that Grignard chemistry, and then in the last step, protonate it using aqueous acid. Okay, again, either one of those is perfectly legitimate. I got no problem with either of those at all. Okay, so a little bit of synthesis, something old and something new in these questions here. And let's look at another reaction of a carboxylic acid, and that's the reduction of a carboxylic acid. You might remember that earlier on we talked about lithium aluminum hydride and sodium borohydride as being reducing agents. And if you take a carboxylic acid and you treat that with sodium borohydride in a polar protic solvent like methanol, you get no reaction, nothing happens, no dice. But if you treat it with lithium aluminum hydride, it's a stronger source of hydride ions, and so it's a stronger reducing agent, and it's going to reduce that carboxylic acid to a primary alcohol. And there you go. So there's another reaction that you can do with a carboxylic acid, is to reduce it to a primary alcohol. And then what can you do with an alcohol? I don't know, Williamson ether synthesis, all kinds of different things. Now, something I've told you many times in this class, and is that a good organic chemist, he should always have more than one way of affecting most transformations in organic chemistry. So another way to reduce a carboxylic acid, and it's not just for the sake of learning, reaction after reaction. Is there, let me fix that. Where's my pen? Is there another way? It's a question we want to ask. Right, and the answer is yes. And again, it's not just for the sake of, making your life more complicated. There's a good reason why you might want to know another way. It says here that we can use borane, BH3. Okay, borane is the common name, borane. We can use borane. The systematic name would be boron trihydride, but we would never say that. So borane can be used instead of lithium aluminum hydride, and it is chemoselective for the carboxylic acid. And if you can't remember, if you need to have me jog your memory what chemoselective means, all chemoselectivity means is that it allows for the reduction of a carboxylic acid in the presence of other carbonyl groups. So it says here of an ester or aldehyde, or a ketone. So BH3 and THF together are going to reduce a carboxylic acid in the presence of any of these carbonyl compounds. And here we have a ketone, and it is untouched by this reaction. So we treat it with borane and THF, and we do the reduction. Now, the mechanism of this reaction is beyond the scope of our class. It is not covered at all in our textbook. But again, it's a good reaction for you to be aware of because you can see that it's so effective. I mean, think about it. If you have a carboxylic acid that you need to reduce in the presence of, let's say you had an aldehyde and an ester in the same molecule. Well, hey, you just go to the cupboard, grab some borane, and just go for it, Very handy-dandy reaction for the organic chemist. Something to have in your toolbox, so to speak. Okay, well, with all that news in mind, and I know that, I've kind of introduced quite a few new reactions this morning. How would we take bromobenzene and and convert that into this compound called benzyl alcohol? And you can see the next reaction is taking toluene and converting it into benzyl alcohol. And the way that we would do the first reaction is we're growing the carbon skeleton, right? We're going from something that has 6 carbons to something that has 7 carbons. Remember, we can't do an SN2, right? We can't treat this with sodium cyanide. That's SN2. That is not going to work. So not an option. But something that is a good option would be to treat this with magnesium, right? With magnesium and diethyl ether, and then we could make phenyl magnesium bromide, and now we have a good. So let me just write it like this: phenyl magnesium bromide. Now we have a powerful nucleophile to react with a good electrophile, like carbon dioxide. So if I treat that with carbon dioxide in the first step and H3O plus in the second step, then I could produce benzoic acid. Now, I don't have to worry about chemoselectivity here for this reduction. I could either do this as a 2-step process. I could treat it with LAH, and then in the second step, I can treat it with acid or water. Usually in the book, I can't remember. Sometimes he says acid, sometimes he says water. Either one is fine. But for this step, now you know that you could use borane and THF. Okay, so either one of these strategies is completely reasonable. And in the second question, there's probably several answers here. If we want to take toluene, which has 7 carbons, and then we want to make benzyl alcohol, which also has 7 carbons, we can't introduce a carbon, so that Greenyard chemistry is out of the question. What else? The cyanide chemistry is out of the question, right? Because those add carbons. But we know that we can add a bromine by treating this with NBS. Okay, so if we treat this with NBS, and if we heat that up, we can do a benzylic bromination. So there's our benzylic bromination, comme ça, as we say in French. Oops, like that. So now we have benzyl bromide. And I'm sure that a lot of you are just saying, Mr. Deon, couldn't you just do an SN2 here with sodium hydroxide? Okay, and the answer is absolutely. Okay, absolutely you could do that. Now, if you're wondering, is there another way to do this chemistry? Because you can do a benzylic oxidation because you do have, 3 benzylic protons here, right? So I would say a second option is just to oxidize this using chromic acid. Okay, so we're going to make that in situ from sodium dichromate, sulfuric acid, and water. Then once you've made benzoic acid, you can simply reduce that by treatment with LAH, and then finally with water, like that. And those are all perfectly reasonable ways to synthesize these compounds.